Hi everyone, my name is Yumeng He. Today I'll be presenting our drawing work with Chandra and Sri. 3D printing is everywhere. Even the consumer desktop printers are used in fields ranging from medicine to everyday products. But the pictures shown here are not always what ordinary users would experience. In reality, many problems can occur in the printed objects. For example, on the left, you see the designs that users wanted to print. These were processed by software and then sent to the printer. But on the right, the printed outputs actually look quite different from the designs. In fact, many printing failures actually come from software bugs. For example, here we show the model that is passed to a slicer, and you will see what a slicer does later. But on the right, you see the preview of its output, which shows what the expected output should look like. And you can already tell the top right corner is going to print wrong. In another case, the original preview on the top looks already pretty bad. But when we try to apply some software to fix it, the result is even worse. More parts are missing. So today, I'm going to talk about how can we catch real-world failures that are actually caused by software bugs. And let's begin by taking a look at the 3D printing software pipeline. So first, users can work with CAD tools to design the objects they want to print. And the design is exported as a triangle mesh, and users may use mesh tools to manipulate or repair the mesh. And next, the slicer takes the mesh along with a bunch of parameters and converts it into G-code, which is the printer instructions. And finally, the printer executes those instructions, extruding filament layer by layer. And if everything goes right, we'll get this cute bunny, which matches the original model perfectly. But if something goes wrong, then the problem can be traced back to any of the earlier stages. For example, the model design itself might just be flawed. It can have some small, intricate features that are simply not suited for printing. The mesh could also be invalid at the geometry level. The slicer could also be buggy in handling certain geometries and thus producing incorrect G-code. So how can we catch bugs in this early pipeline? We can have separate checkers for each stage. For example, finite element analysis for the models, mesh repair tools for the mesh. However, there's still no dedicated checker for the G-code. And by filling this gap, we also realized that by checking G-code, we can also find problems in the previous stages, because those errors all eventually show up in the G-code. And now that we've decided to analyze on G-code, we can apply differential testing directly on it to find bugs. For example, to find bugs in slicers, we can check if two slicers generate the same G-code for the same model. And if they don't, then at least one of the slicers is buggy. For mesh repair tools, we can compare G-codes before and after applying the tool to see whether it fixed a problem or if it introduced new problems. For the models, we can check whether G-codes from the same model but under different conditions, like different orientations. And if they differ, then the model could be buggy. So in every case, applying differential testing comes down to comparing two G-code programs. And since G-code is essentially a set of instructions telling the printer how to move and extrude the filament, what we really care about is whether two G-code programs are semantically equivalent, meaning that they actually represent the same object. And to make that possible, we first need to define the semantics of G-code. Basically, G-code is instructions telling the printer how to move the nozzle and then extrude the filament. The nozzle is heated, so the plastic can flow through, which is just like squeezing out toothpaste. And to make it easier to model, we treat every piece of extruded filament as a simple cuboid. And now let me illustrate how G-code works. First, G-code is stateful, meaning that after each instruction is executed, the program state changes. And this state has two components, the current nozzle position and a set of cuboids representing the constructed object. And let's start with the first instruction. So every movement instruction in G-code starts either with G0 or G1. And here we have a G0, meaning that the nozzle will only move but not extruding any filament. So after this instruction, the nozzle will move to position 100.2, but with no extrusion. And for a G1 instruction, the nozzle will not only move to a new position, but also extrudes filament along the way. So after this instruction, the nozzle will move to the new position, but also extrudes filament. So there is a new cuboid being added to the cuboid set. And the remaining two instructions are processed in the same way. And finally, the nozzle returns back to the starting point. And there are 3 cuboids in the cuboid set representing the current constructed object. And at the end of this process, we'll have a set of cuboids whose union represent the G-code program. And so now, if we want to compare 2 G-code programs, we could just simply take 2 such unions and compute their solid geometry difference. Sadly, this approach doesn't scale. For example, for this Warrior model, it already produces around 138,000 cuboids. Therefore, we decided to sample each cuboid into points, producing a point cloud for the G-code program. So now, comparing 2 G-code programs becomes comparing 2 point clouds, and this is the core idea behind our tool, which is called Glitch Finder. So as an efficient G-code diff tool, Glitch Finder goes beyond simple point cloud comparison and tackles several challenges. First of all, to compare 2 point clouds, the most straightforward way is to compute the Hausdorff distance, which will give us a number to measure the difference. But the problem is, a single number couldn't tell us where the errors happen. So instead, Glitch Finder segments the point cloud into unit boxes and compare them box by box. In addition, Glitch Finder tackles 3 more challenges: floating point errors that happen in segmentation, quantization, and discretization errors, and how can we highlight the largest errors. And Glitch Finder addresses them by introducing what we call augmented Hausdorff distance, combined with spatial averaging and thresholding. If you'd like to know more about the details, please go read the paper. So the output of Glitch Finder is a difference heat map. The color intensity indicates the magnitude of differences. So for this model, the cape region inside the red box has the darkest color, meaning that this area is most likely to print wrong. For our evaluation, we show that Glitch Finder is able to detect both model bugs and software bugs. And let's start with model bugs. So intuitively, a model should slice the same way no matter how it's oriented in the slicer. And more formally, if we have a model and we slice it to get the G-code, and when we apply some rotation on it and we repeat the same process, the 2 G-code programs should represent the same object after aligning their orientation. But if they don't, then the model often turns out to be buggy. So the motivation for this actually came from GitHub issues from popular slicer repositories. We noticed that users commonly check if the same model sliced the same way, but in different orientations. And especially after they discovered that the original orientation has some problems. And by checking this property, Glitch Finder successfully found issues in 56 buggy real-world models. Specifically, Glitch Finder can find common mesh issues, like mesh with fluid normals and mesh that are not watertight, which are the problems that mesh repair tools are designed to handle. So we show one example for each case, and in both cases, the heat maps correctly highlights the problematic regions in the original orientation. Glitch Finder also finds a new class of bugs, which are models that have features that are too small to print. These issues are not detected by mesh repair tools because the concept of smallness is relative to the slicer and its parameters, but not a problem in the model itself. But in contrast, Glitch Finder can find this problematic thin wall design in the heat map. And the other application is to find software bugs. And first is slicer bugs. Glitch Finder compares two slicers, Cura and Prusa slicer, and has verified that in most cases they behave the same, but in some cases they differ. For example, here you can see the Prusa slicer generates incorrect G code at the area which is highlighted by the heat map. And second is the mesh repair toolbox. So we evaluated on two popular mesh repair tools, and Glitch Finder helps us to detect if the tool actually fixes a problem or not. So we showed this example earlier also. You can see in this case, not only the tool failed to repair the model, but also introduced new problems. And anything we don't have time to cover today is in the paper. If you'd like to know more about how we distinguish between true positives and false positives, and also the running time analysis, I encourage you to read the paper. So in conclusion, we introduced Glitch Finder, which is a new tool for G-code differential testing. It defines new G-code semantics with cuboid sets and uses an efficient point call-based diff that help us to find bugs in both models and fabrication tools. Thank you very much.
Let's take a couple of questions.
Hi. Harry Goldstein, University at Buffalo. This is awesome work, really like it. I had one technical question, which is that when you're printing, if you print two lines out of order, the points or the cuboids, in my mind, seem like they would be the same, but printing-wise, they would be very different. Do you take a look at the order that the points are created, and or how do you deal with that?
I'm sorry, in what way they're different?
So when if the 3D printer tries to print a layer that is too high, and then the layer below it, it won't work. And so those the G code is, but the points that they're printing is the same. Does that make sense?
So you're saying something happened in the printing stage?
I'm saying let's say we can also take this offline, but you've got G code that prints some plastic and then a line of plastic above it. And then you've got some G code that prints the higher one and then the one below it, which obviously isn't going to work.
So they're different, definitely.
Okay, so it would be different even though the points of those two are the same.
Yeah.
Okay.
Yes.
Thank you.
Hi, Roger Burton Patel, University of Pennsylvania. I have a question about the printing pipeline. So would it be possible to go back to the slide where you show the various places that things can go wrong? Great, yeah, thank you. Can anything go wrong in the G-code to printed objects step? And did this ever trip you up? Or is this sort of the hardware print, is that relatively robust?
So many problems can occur in the printing step, but our work is focused on the software. Yeah, absolutely. I'm just curious if things that went wrong in the print step ever made you feel like the tool wasn't working, but it actually was just that something else was going wrong. Yeah, so we're now focusing on the problem which happened in the printing step. Yeah, okay, that makes sense. Thanks. Thank you for the question.
Thanks for your talk. I think it's a very interesting topic to use static analysis technique in the 3D software, 3D printing software. And I would like to ask, do you think is it an easy task to integrate all this system into some real-world software?
Yeah, so this should be useful in differential testing of fabrication tools. Software developers can use them to test their software to check their correctness. And also our tool is pretty automated. So now the implementation of this just takes the model and then you can tell it what orientation that you want to compare against. And so it would just generate a heat map automatically. So it should be very easy to integrate into other pipelines.
Last question for me. What happened to all those bugs? Did you submit them? What were the reactions to them?
Actually, no. I think I reported one to the Certora repository, and they have some experimentation, but no, like, yeah.
Okay, well, let's thank the speaker, and thank you for coming to this session.